It sounds impossible. Throw around 100 million cubic meters of sand into the open sea and expect it to hold roads, hotels, villas, and thousands of people. But Palm Jumeirah was not built by simply dumping sand into the Gulf. The real challenge was hidden below the waterline. Choosing the right sand, placing it with GPS-guided precision, locking it into a dense foundation, and then protecting it from waves that would spend decades trying to take it back. This is how Dubai turned loose seabed material into one of the most recognizable artificial coastlines on Earth. Palm Jumeirah pushed Dubai's shoreline from a narrow strip of coast into a luxury destination, and the island itself mattered less than the extra waterfront it created. The project extended Dubai's usable coastal edge far beyond its natural 72 kilometers. Dubai in the 1960s looked nothing like the skyline known today. The city stood beside a trading creek near the Arabian Gulf, and oil money fueled much of its growth through the following decades. By the early 2000s, Dubai's leadership understood that long-term growth could not rely on oil alone. Tourism became the new target, but another obstacle appeared immediately. Dubai only had about 72 kilometers of natural coastline, and luxury tourism demanded beachfront property on a much larger scale. A circular island concept first increased the beachfront by only 7 kilometers. The proposal failed to satisfy the scale Dubai wanted. The Crown Prince Sheikh Mohammed later sketched a palm-shaped island that expanded the coastline to roughly 56 kilometers. The design stretched 5.5 kilometers into the Arabian Gulf with a trunk nearly 2 kilometers long, commonly described as having 17 fronds, and a crescent-shaped breakwater surrounding the outer edge. After several years of feasibility studies, construction officially began in 2001 with large-scale land reclamation operations. The island needed around 94 to 110 million cubic meters of sand and 5.5 million cubic meters of rock. Engineers compared the total material volume to a wall circling Earth at a height of 2.5 meters. To put that into perspective, no private developer had ever attempted moving that much earth material into the sea before. Dutch reclamation specialists joined the project because the Netherlands had already expanded its own landmass through reclamation work. Research teams studied wave height, tidal behavior, sea level rise, and the winter Shamal storms. Environmental modeling included long-term coastal stability projections across decades. The breakwater became the project's shield against erosion and violent seas. Engineers calculated that the protective barrier needed to stand at least 3 meters above the waves, while stretching 11.5 kilometers around the island. Construction crews opened operations at 16 quarries across the UAE. Rocks weighing up to 6 tons traveled non-stop from mountain blasting sites toward the coast. Barges delivered nearly 40,000 tons of stone every day. Each rock layer followed precise placement rules to maintain structural interlocking strength. The contrast between extraction sites and offshore formation highlighted the scale of material movement involved. The island itself rose from sand dredged 6 nautical miles offshore. Giant dredgers filled 8,000-ton tanks before spraying sand through pipes at 10 meters per second in a process called rainbowing. GPS technology guided the placement because nearly every section of the island followed curved geometry. A single misplaced load could throw off the curvature of an entire frond, so accuracy mattered more than speed. Engineers also raced against a compressed timeline. Similar projects normally required around 15 years, but Palm Jumeirah's mainland platform rose in only a few years. Time constraints forced parallel construction across multiple zones of the island. The reclaimed land created an engineering challenge because loose sand could liquefy during earthquakes. The 2003 BAM earthquake in Iran demonstrated how reclaimed land can suddenly lose strength during seismic movement. Palm Jumeirah therefore required deep stabilization before large buildings could rise above the surface. Subsurface densification reduced long-term settlement risk across the platform. Another danger emerged after construction had already advanced far into the Gulf. Water circulation inside the palm structure moved too slowly, creating fears of stagnant water and algae growth. Hydrodynamic flow became a key design parameter after initial circulation analysis. Computer simulations revealed that the crescent barrier needed 2 openings connected by 4-lane bridges. Those gaps allowed tides to flush fresh seawater through the channels twice daily. Fresh seawater moving through those narrow openings ended up carrying the survival of the entire island community. Water exchange cycles became essential for maintaining marine balance inside the structure. Over 850 buses transported a 40,000-strong workforce daily across 2 12-hour shifts to maintain construction pace. Millions of tons of imported steel and concrete were coordinated through global supply chains, feeding directly into the island. Contractors installed roads, water systems, gas pipelines, electrical infrastructure, villas, apartments, shopping centers, and hotels across the reclaimed surface. The trunk alone later expanded with plans for apartment towers, retail districts, and luxury developments. Infrastructure layering required synchronized delivery of multiple utility systems. Environmental concerns remained under constant review throughout construction. The Palm Trunk expansion supported infrastructure value equivalent to multiple billion-dollar construction phases. Engineering management emphasized real-time adjustment of plans as project scope expanded beyond the original 60,000-person capacity target. By mid-development, housing capacity planning doubled after demand pressure from early buyers exceeded initial forecasts. What started as a real estate project quietly turned into one of the largest privately funded engineering operations of its time. Around 2007, the first phase of residential delivery started, introducing approximately 4,000 luxury villas and apartments to the market. These properties were released in stages to match infrastructure readiness and coastal stabilization progress. Over time, tourism, retail, and leisure facilities were added, reshaping the island into a mixed-use destination. The combined development has positioned the site as a globally recognized landmark for coastal engineering and high-end waterfront living. Palm Jumeirah also triggered larger ambitions. The project is the first component of a larger coastal expansion concept known as the Palm Trilogy. Palm Jebel Ali, Palm Jumeirah, and the artificial archipelago known as the world expanded Dubai's coastline vision even further. Together, the projects aim to increase Dubai's waterfront from 72 kilometers to nearly 1,500 kilometers. Hotels, beach clubs, marinas, restaurants, residential towers, and shopping centers were layered into each project, turning these islands into small coastal cities rather than simple real estate developments. Palm Jumeirah ultimately became more than a luxury island. It represented Dubai's attempt to replace a future beyond oil with tourism, engineering spectacle, and coastline created directly from the sea. The moment the first fronds of Palm Jumeirah broke the surface, the global real estate market witnessed an explosion of demand unlike anything seen before. Early residential units reportedly sold out within 3 days, and celebrity buyers including David Beckham attracted even more attention toward Dubai's new coastline. More than 4,000 villas and apartments eventually appeared across the project. Real estate absorption rates exceeded initial economic projections. Some waterfront villas were listed around $1.2 million at launch, reflecting immediate high-end market positioning. Over 8,000 residential units were planned along the 1.6-kilometer trunk section, making it one of the densest luxury corridors in the project. Around 220 commercial and retail spaces were integrated into the trunk development plan, increasing overall property yield per kilometer. Fueled by the massive success of the first island, Dubai's engineers set their sights on an even more ambitious sequel. Palm Jebel Ali is an island designed in a palm shape, similar in concept to Palm Jumeirah, but planned on a larger overall scale. A surrounding crescent acts as a protective barrier while also hosting waterfront communities designed for continuous ocean access. The layout prioritizes sea views, marina access, and open space integration, turning the shoreline into a controlled economic asset rather than a fixed natural boundary. The project expands usable coastal length while connecting land, sea, and urban life in one unified design. The layout stretched the coastline farther, creating roughly 10 to 15 kilometers of extra waterfront potential compared with Palm Jumeirah. While Palm Jumeirah is already fully developed with luxury hotels and residential zones, Palm Jebel Ali remains a testament to long-term vision, standing in partial development stages as its future potential continues to grow. But Dubai's ambition didn't stop at palms. They wanted to bring the entire planet to their shores with the ultimate offshore vision: the world islands. This is an artificial archipelago constructed from dredged sand, arranged to resemble a world map when viewed from above. The development consists of around 300 small islands separated by water channels that function as natural navigation routes. Some islands are designed for private estates, while others are planned for resorts, residential zones, or commercial use. Construction began in 2003, but progress slowed sharply after the 2008 financial crisis. The world islands remain largely conceptual in parts, but they represent Dubai's broader strategy of turning open sea into customizable real estate. Reclaimed islands like the Palm Islands didn't just appear out of ambition. They emerged from a confrontation with the sea, and the sea does not give ground easily. To understand how engineers turned millions of tons of unstable sand into the foundation for an entire city, we have to go below the surface, to where the real engineering begins. It sounds like a paradox, building a sand island in a country that is almost entirely covered by a desert. Scan the desert surrounding Dubai, and the scale of available sand becomes almost incomprehensible. Dunes stretching past every horizon, billions of tons sitting untouched. But none of it built Palm Jumeirah. Wind-blown desert sand is often rounded and smoothed over long periods, reducing the mechanical grip between grains. Seafloor sand never experienced that exposure. Buried beneath salt water, edges stayed sharp, surfaces stayed rough. The secret behind this engineering choice only reveals itself when we look closer than the human eye ever could. Building sand and desert sand look nearly identical to the naked eye, but the difference only appears under magnification. Angular grains from the seabed interlock under load, effectively spreading weight across the structure like a microscopic jigsaw puzzle. A microscopic view of sand reveals grains rolling like glass beads under magnification. Desert sand appears smooth, but those rounded particles slide past each other, weakening foundations for artificial islands. Weaker cohesion leads engineers toward angular sand sourced from offshore seabeds instead of desert dunes. The hidden behavior of these tiny grains determines whether the ground can hold a massive structure or collapse under the slightest movement. Understanding this microscopic geometry is what allowed engineers to turn loose seabed material into stable reclaimed ground. Selecting marine sand is not just about volume. Engineers analyze grain size, density, shell content, and sediment composition to make sure the reclaimed ground can compact evenly and remain stable under long-term structural loads. The stability of a multi-billion-dollar artificial island depends not just on how much sand is placed, but on how that sand behaves under pressure, water movement, and long-term structural load. The focus shifts to coarse, angular seafloor deposits that provide superior structural integrity against relentless tides. The way these grains interlock helps the reclaimed ground support roads, utilities, villas, hotels, and dense waterfront development. Every cubic meter is vetted through rigorous gradation tests to ensure it can withstand the constant forces of the open ocean. Mapping invisible underwater terrain gives engineers something to build from, a known seabed instead of an assumed one. The choice of borrow area is not administrative. It determines whether the ground beneath the island holds or shifts. Before any sand can be dropped, surveyors must first strip away the mystery of the deep by visualizing the complex landscape hidden beneath the waves. Layered seabed maps gradually reveal underwater slopes used for artificial island planning and offshore foundation studies. Survey vessels scan more than 10,000 square kilometers of water areas, while sonar and bathymetric systems convert depths from 0 to 300 meters into detailed 3D terrain models. Core sampling equipment drills beneath the seabed to recover sediment layers for geological evaluation before marine construction moves forward. To eliminate any technical uncertainty during this expansion, engineers combine geodetic measurements, LiDAR data, and underwater object detection to create a flawless digital twin of the seafloor. Would offshore reclamation still stay accurate without repeated sound velocity checks beneath the survey vessel? Survey crews using the WASSP multi-beam sonar system trace underwater terrain before reclamation work can move ahead. A GPS antenna positions the sonar transducer, while a secondary antenna maintains accurate heading data across the survey path. Sound waves spread across a 120-degree swath with half-degree beam spacing, then return to the sonar head after reflecting from the seabed. Motion reference data, vessel position, and sound velocity profiles are combined to correct underwater measurements throughout the operation. Crews collect new sound velocity profiles every 6 hours or whenever the vessel enters another geographical section, helping the final hydrographic map remain consistent for offshore planning. The first tool used to build an artificial island is not a crane or a dredger, it is sound. Compressed air pulses fired from survey vessels travel deep into geological layers beneath the ocean floor, mapping rock formations and energy reserves before a single construction decision is made. These ships work between 3 and 200 miles offshore, using hydrographic sonar to trace underwater contours, while acoustic and visual teams monitor marine life throughout the process. A soft start procedure ramps sound intensity gradually, so sensitive species can leave the area before full surveying begins. The data returning from all of this builds into a three-dimensional underground model, less a collection of numbers and more a complete picture of terrain that engineers will eventually force above the waterline. Once the terrain is mapped and the subsurface is understood, the focus shifts to the physical stability of the material through rigorous soil compaction tests. Technicians sieve 4.5 kilograms of fine soil, then mix water contents ranging from 6 to 24% before compacting samples inside a cylindrical mold. Each layer receives 25 hammer blows to measure maximum dry density and optimum moisture content under ASTM D698 procedures. Oh, those compacted sand columns feel like carved stone once the mold is removed. Engineers compare density curves, moisture calculations, and zero air void data to identify seabed zones suitable for material dumping, while unstable sections receive ground treatment first before offshore filling operations move into position. How can engineers move millions of tons of wet earth to literally create new countries out of thin air? It all starts with the fundamental process of dredging, where specialized pumps move sand, gravel, and an abrasive slurry before dehydration systems remove excess water from the collected material. Oh, those thick streams of slurry almost behave like moving wet concrete crossing the pipeline network. This treated sediment later supports flood control and coastal expansion, forming the very foundation of our modern maritime world. But behind every successful dredging operation lies a mechanical heart that never stops beating: the heavy-duty dredge pump. These engineering marvels, handling solids up to 15.75 inches, keep offshore slurry transfer moving without blockage. Solids move continuously beside sand, clay, and gravel without clogging. Thick slurry disappears through the intake like collapsing seabed. While standard pumps handle the flow, the cutter suction dredger acts as the ocean's heavy-duty excavator, capable of chewing through the toughest seafloor materials. This machine uses a rotating cutter head to loosen rock, clay, silt, and sand before high-power pumps pull the mixture on board. The vessel stays fixed on spuds and anchor wires, while side wires guide the cutter head in wide, sweeping arcs across the work zone. The cutter head keeps shaving the seabed away, while the hull barely shifts position. After one section is cleared, the support spud lowers into the seabed, and the main spud carriage advances several meters forward for another dredging pass. Soil mixed with large volumes of water travels through discharge pipelines toward reclamation zones or barges waiting nearby. During large reclamation projects, continuous dredging cycles can reshape underwater terrain, while coastal foundation levels gradually rise above surrounding sea conditions for expansion steadily. This is where the real weight of the project hits. Hopper vessels release massive sandwater loads onto shallow marine zones, repeated dumping cycles gradually pushing the seabed higher with each pass. The discharged mixture spreads outward in thick currents before settlement layers compact beneath the surface. And what forms below the waterline during this stage looks less like controlled construction and more like an underwater storm rolling across the site. Engineers track depth changes after every release because raw volume alone cannot produce the precise palm-shaped contours the design demands. Grading stages follow, redistributing material, stabilizing uneven sections, and leveling the platform before anything permanent can go in. As the foundation reaches the surface, the process turns into a spectacular display of engineering known as rainbowing to shape the land directly above the water. The airborne slurry almost looks like a moving shoreline, stretching farther with every discharge pass offshore. Rainbowing rapidly builds visible reclaimed terrain before final stabilization and contour refinement continue. A dredging vessel working miles from shore has no landmarks, no road markings, no visible reference of any kind. But the shape it leaves behind matches the original design close enough to build on. Differential GPS makes that possible by pairing satellite signals with fixed onshore reference stations that continuously correct positioning data in real time. Every adjustment feeds directly into the vessel's navigation system, keeping the dredger locked onto its designed route as sand placement follows each frond in curved shoreline. GPS satellites, reference stations, and onboard receivers work as a single system, and together they turn featureless open water into a coordinate grid precise enough to build a city on. Multi-beam sonar survey maps seabed layers during reclamation operations. Reclaimed sand arrives loose and saturated, structurally unreliable until vibro-compaction forces the particles into place. A vibrating probe drives into the fill, while water jetting clears weak soil ahead, letting backfill lock tightly around the vibrator zone by zone. What was waterlogged fill becomes ground stable enough to build on. Adding sand builds volume. It does not build strength. Vibroflotation closes that gap by running vibration probes through a structured grid across the seabed, compacting sand into dense columns layer by layer. Operators control penetration depth to hit target density in each zone, and repeated passes eliminate the voids that loose fill always leaves behind. The ground that comes out of this process can actually hold what gets built on top of it. Compaction does not stop when the vibrator lifts out. That is when the real monitoring begins. Operators track density readings after each cycle to identify zones where particles have not packed tightly enough, then target those areas for additional passes or corrective filling. Ground settlement visible at the surface confirms that deeper structural changes are happening below. Data collected at every stage of this process determines where the foundation is ready and where it still needs work before platform construction can continue. Beneath a finished artificial island runs a hidden grid of sand columns, the part of the structure no one ever sees, but everything above depends on. Vibro-flotation builds them by driving a vibrating probe deep into loose, reclaimed fill, the vibration forcing surrounding particles to collapse inward and repack into dense vertical columns. Water jets clear weak material ahead of the probe, while sand backfill drops in from above, locking each column in place as the rig moves through a structured grid across the site. Repeated insertions build uniform ground conditions across the entire foundation zone. The island above carries roads, buildings, and thousands of residents, but what keeps it from sinking is a silent forest of compacted sand columns extending deep into the seabed below. Have you ever wondered how engineers prove that a pile of loose sea sand has actually turned into a solid, skyscraper-ready foundation? Observe this testing demonstration. Technicians perform penetration testing by driving the cone downward and recording travel depth through compacted material. Before heavy structures go in, engineers need to know how the reclaimed ground actually behaves under load, not how it looks. The Sea-Calf cone penetration system pushes an instrumented probe directly into the seabed, measuring tip resistance and sleeve friction in real time as it descends through each soil layer. The data coming back tells engineers where the ground is dense enough to build on and where it still needs work. While sensors provide the numbers, sometimes engineers need to reach down and touch the physical evidence of the Earth's strength. Engineers drill through multiple underground layers to collect soil samples before artificial island construction proceeds. Tests later evaluate how submerged soil reacts under structural loading conditions. Imagine building a fortress using nothing but grains of sand and expecting it to survive the raw power of the open sea. Artificial island coastlines remain exposed until breakwater construction absorbs enough wave energy to protect reclaimed sand permanently. Engineers construct layered mound breakwaters using rock and reinforced superstructures surrounding exposed offshore sections. Incoming waves lose force long before reaching the protected inner coastline. Some sections rise above the waterline while reinforced foundations sit below it for additional offshore stability. The calm water that forms behind a finished breakwater is not an accident. It is the result of every layer doing exactly what it was placed there to do. Before any armor rock arrives, the seabed beneath the breakwater needs its own foundation first. Core stone filter layers and geotextile barriers go down directly onto the submerged base, while marine mattresses spread load across the bottom to prevent uneven settlement. Everything built above the waterline is only as stable as these buried layers underneath. Lowering a 10-ton block onto the seabed from a crane wire is only half the problem. Placing it within centimeters of its intended position is the other. Marine positioning systems guide each armor block along the exposed perimeter of an 11-kilometer crescent breakwater, ensuring no gap forms between placements that wave pressure could later exploit. Offshore reefs and protective blocks descend by wire crane, while real-time positioning data keeps the crew on target through currents, wind, and low visibility. A single misplaced block does not just create a weak point, it creates an opening the sea will find. More than 70,000 tons of granite and 280,000 tons of limestone. And none of it is meant to stop the sea completely. Water pushes into gaps between armor rocks, where turbulence and friction drain energy from each wave before it can travel further. Additional reef structures positioned roughly 100 meters offshore intercept incoming motion before it even reaches the main barrier. The breakwater does not fight the ocean by blocking it. It dismantles each wave from the outside in, layer by layer, until nothing dangerous reaches the shoreline behind it. Once the armor is set, the transformation is immediate. The violent white foam of the open ocean turns into a calm blue mirror on the other side. Wave energy weakens dramatically once layered armor rock surrounds the reclaimed shoreline. Massive rock blocks are positioned across the breakwater, while smaller layers lock gaps beneath them. Some sections look like a stone wall floating against open water. Engineers even use nature against itself, letting the currents build the defense along with the island. In this case, more than 700 meters of sandbar breakwater were formed using natural coastal sand movement, allowing the protective structure to grow together with the expanding port edge. Along the marine construction zone, dredged sand continues building the shoreline, while parallel rock barriers rise beside it to control incoming currents. Coordinated placement between dredging vessels and breakwater crews keeps the reclaimed perimeter stable, while additional fill material expands outward. The crescent-shaped defense eventually becomes more than shoreline protection because the long-term survival of artificial islands depends on keeping wave erosion away from the reclaimed foundation. The entire coastline practically leans on that outer barrier for protection every single day. In offshore artificial structures, maintaining lagoon circulation becomes far more complex once transport infrastructure interrupts natural water exchange. Water circulation becomes a critical design factor when artificial islands and connected structures form semi-enclosed lagoon systems. Open channels between land sections allow tidal flow to move through instead of stagnating, preventing pollution buildup. Bridge tunnel layouts help maintain exchange between ocean water and inner lagoon zones. Each gap in the structure is a deliberate design decision, not an oversight. Aerial perspectives reveal that blocking waves completely does not guarantee a stable internal water environment. The bridge system shows the challenge of balancing wave exclusion with internal lagoon circulation around a reclaimed island water body. Continuous monitoring adjusts flow balance during changing tidal conditions constantly. The system carefully balances protection and water exchange to prevent internal ecosystem collapse. Getting the circulation right is not guesswork. It starts with hydrodynamic modeling long before construction begins. Hydrodynamic models guide water flow design inside artificial lagoon systems to maintain circulation and prevent stagnant zones. Water flow keeps the lagoon alive, but structural monitoring is what keeps the island standing. Beyond circulation, the long-term stability of artificial islands depends on continuous measurement of settlement and structural clearance. Heavy cargo vessels carrying construction cranes must pass under bridges with precise air gap calculations, supported by real-time oceanographic data systems. Tidal height, current velocity, and seabed conditions are continuously measured to guide safe navigation through narrow waterways. These measurements are also essential for maintaining dredge channels and ensuring that reclaimed coastal zones remain operational over time. Continuous sediment shifts around bridge foundations and harbor entrances require repeated adjustment to preserve navigable depth and structural safety. Coastal erosion does not wait for construction to finish. It starts working against the shoreline the moment reclaimed sand settles. Engineers monitor long-term stability continuously across bridge tunnel structures and nearby coastal zones, tracking how persistent wave energy gradually reshapes sand foundations over time. Drones and hydrographic surveys now act as the primary eyes for documenting erosion and settlement along protected infrastructure. Routine inspections support long-term stability of reclaimed coastal systems. Erosion pressure remains visible despite protective breakwater structures. Systems adjust maintenance planning accordingly continuously. Finishing the breakwater solves one problem and immediately creates another. Trapped inside a sealed basin, the water had nowhere to go. Without water movement, salinity rises, oxygen drops, and the ecosystem inside slowly collapses. Engineers had built the structure, now they had to keep it alive. The solution was deliberate openings cut into the breakwater, allowing seawater to flow in and out with the tides. That gap in the wall is doing more structural work than most of the rock around it. Monitoring systems track salinity levels and current speeds, fine-tuning the exchange across different tidal cycles. There was no single dramatic solution, just constant adjustments and maintenance happening quietly in the background. Construction did leave marks elsewhere. Dredging altered tidal patterns along nearby coastlines, and some marine habitats took years to stabilize. The islands also require continuous monitoring for gradual subsidence. These weren't ignored. They became part of the maintenance framework that keeps the project functional decades later. The Netherlands Delta Works and South Korea's Songdo point to the same conclusion. The projects that hold up are the ones that treated maintenance as part of the design, not an afterthought. The Palm Islands reshaped a coastline. What they taught engineers may matter even more. Monitoring identifies the problem. Maintenance dredging is what actually fixes it. Long-term dredging cycles, not initial construction, keep a man-made coastal lagoon system functioning as erosion continuously reshapes the seabed beneath it. Repeated sediment replenishment prevents lagoon channels from closing, while hydrodynamic forces redistribute sand across the reclaimed floor. The island above looks unchanged. The work keeping it that way never stops. The success of an artificial coastal beach depends on post-construction stability more than the initial build phase. Post-construction stability work, shoreline grading, sand replenishment, and depth corrections, keeps recreational coastal areas functional years after the initial build phase ends. Life continues smoothly on these engineered sand foundations. Residential towers, transport corridors, and active waterfronts all operating on ground that did not exist a few decades ago. Long-term settlement control systems keep infrastructure stable, while continuous monitoring maintains structural balance across the reclaimed platform. The real challenge is not creation, but endurance. Artificial islands like the Palm Islands stand as long-term engineered coastal systems where land reclamation, breakwaters, and sediment control work together to maintain artificial shorelines over decades of ocean pressure and environmental change. What appears finished is actually a continuously managed hydraulic system. More than a construction project, the system behaves like a living coastal machine that must adapt to tides, storms, and long-term geological settling. Salinity balance, sediment movement, and shoreline shifts require constant observation to preserve structural integrity. Transport, residential zones, and coastal defenses all rely on the same underlying engineered ground behavior to remain functional. While dredging and seabed modification may temporarily affect marine habitats, modern planning increasingly includes mitigation strategies that support ecosystem recovery and biodiversity protection. In some cases, artificial islands also create new sheltered water zones that can benefit navigation, coastal protection, and even support new marine habitats. Palm Jumeirah is often remembered for its shape, but the shape was only the visible result. The real achievement was the system beneath it: selected sand, surveyed seabed, GPS-guided placement, compacted ground, protective rock, and water that still has to keep moving. It was not simply land reclaimed from the sea, it was land that had to be engineered, defended, and continuously maintained against the sea trying to take it back.